What's going on, Principles of Engineering engineers? This is Mr. Suffering here, and today I would like to continue our discussion on moments and rotational equilibrium. So let's get to it. So important points we have covered. We talked about moments. We talked about the formula of moments. A moment equals force times the perpendicular distance. And when we're talking about rotational equilibrium, we need to understand that the sum of our moments must equal to zero in order for our beam to be in rotational equilibrium. Okay, so going back to the previous problem, and here we go. We have a beam. Okay, this beam has a force, right? And that force is 35 pounds. Okay. This beam also have two joints, joint A and joint B, and it also have two pins. Okay. And another important point that we've discussed is that we've talked about pins, and we also talked about rollers. And a pin has two reaction forces. One reaction force going in the X direction and another reaction force going in the Y direction. Okay. And a roller has one reaction force. Okay. So, but in this case, we have two pins, right? So we have two reaction forces. Okay. And what I'm going to do, I am going to erase my pin connection and replace that pin connection with two reaction forces. So we have a reaction force going in the Y direction, and we have a reaction force going in the X direction. And be honest with you, we don't know what direction this reaction force is going in the X direction. We just picked a direction and we also just picked a direction with our, well, we actually know what direction our reaction force with regards to the Y direction, but we don't know what direction the reaction force is going in the X direction. When we're calculating trusses, we can actually guess, what direction this reaction force is going, and then we can let the math, tell us what direction it is going. And we will have more examples as we continue on. So I'm going to erase this pin connection, and we're going to replace it with two arrows indicating the reaction force. Okay. And what we're going to do, we're going to solve for the reaction force at joint B. So what we're going to name these two reaction forces, since these two reaction forces are on joint A, we're going to call this reaction force A going in the X direction. Okay. And this reaction force right here, we're going to call this reaction force A going into the Y direction. And just like what we did with joint A, we're going to do with joint B. We're going to name this reaction force R, reaction force at joint B going in the X direction. And we're going to name this reaction force at joint B going into the Y direction. And what we're going to do, we're going to solve for RBY. Why not RBX? Because you're about to see the X reaction forces are going to cancel out. And I'm about to show you that, okay? So if we're going to solve for RBY, we need a pivot, okay? And our pivot is going to be at joint A. So I'm just going to put a larger dot right here. So here's what we have. We have joint A, we have joint B. We have our pivot at joint A, and force C, okay, force C, and I'm just going to name that. I'm going to name this force at force C. Okay, so force C is 3 feet from our pivot. Okay, and joint B is 10 feet from our pivot. Okay, and what I'm going to do is write the formula for moments. So we're going to say the sum of moments equals 0. And we're going to do this. We're going to say, hey, around joint A. Okay, so the sum of moments equals 0 around joint A. Okay, so we already know our moment equals force times the perpendicular distance. So what we're trying to do, we want to know all the moments for each force acting upon joint A. So with that being said, we have a possible moment at force with force, reaction force AX, okay? Plus, we have a reaction force at RAY, or I'm sorry, we have a possible moment at RAY. We also have a moment, possible moment at force C. We also have a moment, could have a moment at reaction force B going in the X direction. We also can have a moment at reaction force B, reaction force at joint B going in the Y direction. And all of those moments must equal to what? Must equal to 0. Now, since our moment equals force times the perpendicular distance, okay, so we have a force, RAX. We have force RAX. Okay, we don't know the magnitude of this force, but what is the perpendicular distance of RAX from joint A? Okay, absolutely. The perpendicular distance is 0. Okay, so let's take a look at, one more important point I didn't mention that we did mention in our last class meeting, that you can have clockwise moments and counterclockwise moments, right? And so just let me just draw my coordinate system. So let's say we have, all right, Y, we have our X. Okay, so this is our Y, this is our X, and we know a positive moment is going counterclockwise. Let's draw this differently. So a positive moment is going counterclockwise, okay? Negative moments are going in a clockwise direction, okay? So with that being said, so we have RBY, I'm sorry, RAY, and it's pushing up at this beam. So if it's pushing this beam this way, this is a clockwise moment. So a clockwise moment is negative, right? But since RAY is located at joint A, let me just write this. What is the perpendicular distance of RAY from joint A? Of course, this is 0. So I'm not going to worry about the negative or positive sign. All right, so we have 4C, okay? So we have a moment at 4C. Now, 4C is 35 pounds. We know the magnitude of 4C. So this force is acting on this beam and is pushing it in a clockwise direction. So we're going to say this is negative 35 pounds, okay? Negative 35 pounds. And what is the perpendicular distance of this force from joint A? It is 3 feet, okay? So we're going to say 3 feet. All right. So we have a moment at RBX. We do not know the magnitude of RBX. So we'll just write RBX. And we're going to say this is positive. We don't know where, if it's pushing it right or left. And what is the perpendicular distance of RBX? It's 0. Okay. Now we have RBY. We do not know the magnitude of RBY. That's what we're solving for. And what is the perpendicular distance? Well, hold on. RBY is pushing up on my beam, and our beam is going counterclockwise, right? And a counterclockwise moment is positive. So we're going to say this is positive RBY. And the perpendicular distance of RBY from joint A is 10 feet. Okay. So now what we can do, we can just go ahead and solve. All of this must equal to 0. So RAX, RAY, RBX, all of those cancels out, right? So what I'm going to do is just go ahead and do the math. So negative 35 times 3 feet, we have negative 105 foot-pounds. Plus reaction force BY, the distance of 10 feet must equal to 0. So now we're just solving at this point. So we can just add 105 foot-pounds on both sides. And now we have RBY, distance of 10 feet, equal 105 foot-pounds. Okay, we divide 10 feet on both sides. That cancels out. Feet cancels out. Now we have reaction force at joint B going in the Y direction equals 10.5 pounds. Okay, so now what this is saying is that in order to keep this beam in rotational equilibrium, we have a 35-pound force going in the clockwise direction. And we have, and to counter that 35-pound force, we have a force at joint B. And that force is 10.5 pounds, okay? So let's say if we wanted to find the force at reaction AY, force AY, okay? So instead of dealing with moments, we can actually deal with forces, right? So the sum of forces is equal to 0. Now, forces are different than moments because moments deal with rotations. Forces just deal with, up and down, left and right. Okay, so we're not going to consider the clockwise and counterclockwise moments because we're dealing with forces. Okay, so if I wanted to find the force at reaction force AY, we can just simply take all of our forces. So we have force RAY, and the sum of our forces must equal to 0. So we have another force at BY. We have another force at force C. Those must equal to 0. Now we can just substitute and solve. So we have RAY plus RBY, which is 10.5 pounds, plus force C. Since force C is going down, we're going to say that's negative. Negative 35 pounds must equal to 0. Now let's just solve. Reaction force AY minus 24.5 equal to 0. Then we can add 24.5 to both sides. And we have reaction force AY equal to 24.5 pounds. Okay. All right, so there we have it. So we have RAY equals 24.5 pounds. We have RBY at 10.5 pounds. And we also have a 35 pound force. So with these forces, we can say that this beam is in rotational equilibrium acting upon joint A. Okay, so let's go ahead and just watch the next video. We're going to talk about calculating truss forces. Okay, we're going to calculate the truss forces, and pretty much all of these principles we went over is applicable to calculating a truss force. Okay, so I hope this helped. So let's go ahead and watch the next video and let's continue learning about our trust forces regarding rotational equilibrium. Okay, have a great day. Peace.